technology. So welcome.
Glad to be here. My first conference after all of this COVID thing. So I'm very happy to be here and meet all of you. The title is very long, but we are going to talk about deep learning to automate processes, to optimize processes in APC and also in RTO type of applications. So if I want to move, I just click.
It's a big green button.
The big green, oh, okay. All right. So we know that AI is going to transform, industries. We are going to be able to optimize, improve, but we need to look at some things where AI can help us. We have tremendous amount of information in process data historians, in LIMS systems. I'm just talking about RTO and IPC. Probably in other types of applications, you have other types of data. And there is a lot of knowledge in that data. So if you don't use it, it's something that you are losing, right? So you can extract dynamic information, you can extract patterns, you can extract many things, and AI can take, let's say, 5 years of data and build a model for you, right? So it could be a static model, or it could be a dynamic model. In our case for APC and RTO, we need a dynamic model. Also, if we use deep learning, if you use the right algorithms, we can capture the dynamics of the process, not only the relationship from input to X to Y variable, but X to Y in the context of time. So that's very important. And also multivariable. So not just only one input to an output, multiple input to multiple outputs, or basically a group of models assembled together to capture a process. And also something that you can get help is in training operators. For example, in the industry, you have people that are experts operating a plant. Other people are not there yet. So you can extract information out of all of the operators to get the best prescriptions and set points for your plant. So if we see the history of process control, we started with the PNID controllers, right, in that first generation to control a single variable. Then we went into the DCS systems, where we are basically taking all of these inputs, accessing actuators, operating the plant better. And then slowly we evolved into the APC, right? These APC systems are really linear models of the plant, which work well within, of course, the limit that they are linear and they will work in certain range. And nowadays, because of all of these modern tools that are available, LSTMs, deep neural networks, it is possible to control the plant and to optimize the plant using these techniques. And we will discuss about this more in depth. So currently we are focusing more into the process areas where you have, let's say, a group of distillation columns, fractionation system, reactor systems, mainly in refining petrochemicals, but we also have some work, done some work in midstream and also in other industries. So everywhere that you have an APC type of problem where you have manipulated variables, controlled variables, and disturbances, this Petuum product can help you optimize the process. So basically the idea is that we have the traditional operation here in yellow or orange, and that operation is really is registered in the process data historian. All of the operators have their own comfort zone. They're operating the plant. We extract the data. We create a dynamic model. And on top of that model, we can do some optimization to find the best way to move at every point from the orange to the blue circle. Of course, considering the constraints of the process, the flow rate, the economics, it could be that you have an optimization function that is economically driven. That's the type typically that is used in RTO, but in APC, the control of the trajectory for a smooth operation and stable operation. So these applications are not only the algorithm itself. So if you just grab an algorithm and put a neural network, yes, you will create some input and output. But in reality, something that will support the company in the long term has to be based on a platform that can scale, that can be used multiple times and can be instantiated. If you have let's say a group of distillation columns, you want to use the first distillation column model and then port that into the platform so that you can continue building. And if you need to do any retraining, you can do it. So a platform basically looks like this. You have first a way to ingest data, and that's the data that you use for training, right? Also, you have a way to prepare this information to validate, and then a way to select models, right? So there is no one single model for every dynamics. So sometimes just a regular neural network will do. Other times you will require an LSTM type of neural network or multiple LSTMs. So different architectures to capture the dynamics of the process. And then later you need to be able to tune because once you have selected that your best model is X algorithm, you want to find the optimal hyperparameters to mimic the process. And finally deploy it and monitor continuously so that when you want to update the model, because let's say that your precision now is not 95%, it's just 89, you can do relearning and retraining. So basically the steps are the prediction phase. So in the prediction phase, you get your data again from the process data historian, from your lab system, and you create a model that will be able to know what is the relationship of each input to each output, and also the disturbances, how they affect the process. Here, this is a real example. I was at the plant when we were doing this application. We're trying to maximize the temperature to increase the recovery and reduce CO2 footprint. And in this case, you see the blue line, that is the actual value. And then the orange one is something in the future. So that's how nicely the system is predicting in the future. So now, if we can predict well, the question is, how do we operate better? So we need to find in the state space the optimal combination of set points. For example, in this case, we have 3 control variables, and then we have around 10 manipulated variables. So what is the optimal condition in order to drive more energy recovery while maintaining the product temperature? So that's the question at every, let's say, 5 minutes. In this case, the application is running every 5 minutes. And then once we go to validation, then we can go into the supervised tier. So in a very high level, the way that we work is we have the Petuum system that has some group of ML models, right? And some logic. You could say that the logic is basically the control logic, where you have your constraints, minimum and maximum values of every variable, for example. And then we pass the values to the DCS, then the DCS takes an action, then we read back, and then we complete the cycle. So it's a very basic closed control loop. The way that we build these models is, again, we get a list of all of the input outputs, MB, DB, CVs. We work with the customer to determine which of these variables we want to maximize, minimize, or stabilize, right? So that's something that the customer needs to tell us. We work with them, they provide the subject matter expertise, and we provide the AI expertise. And then we create this model in order to get this to get these goals within the constraints. Our experience has been, doing different types of implementations. We work in the cloud. We can get this data using our edge data collector, using OPC from the DCS. So the DCS goes into the edge data collector via OPC, then from the edge data collector to a platform using MQTT. And then we can read the data and then write back the results. So this is one of the ways that we can deploy it. The models are trained in the cloud. They can be retrained and they can be redeployed with a minimal, for example, in this case, with a minimal installation on the customer side. And then this is what the operator sees. For every variable, you have one actual measure, and then you are always looking at the forecast of the specific variable. You have also the dashboard in the left, where you are looking at the manipulated variables, control variables, disturbance variables, and you can select which ones you want to activate or deactivate. Let's say that I am an operator and say, I don't want the AI to take control of this variable. I will turn it off and I will control it myself. That's possible, right? So all of those combinations. This is the way we work with our customers. AI is very new in this field. We have multiple projects, but the way that we started, when a customer wants a new proof of concept or a new process or RTO implementation, we go from a step 2 to 3, in which we get the data, we configure the models, we train the models, and then we go back to the subject matter expert from the client side. So we talk, right? We talk and say, is this the correct understanding? Is AI learning the correct thing, right? Once we know that is working, then we put it in operation. At the beginning in open loop, then we go to closed loop, and then finally we just support it, right? So by support meaning the monitoring and any retraining that is done as needed. And these are again a little bit again the phases. When we're working with the customer in the assessment phase, there are multiple variables, but also AI helps us in the feature engineering. You know, there are some variables that we look for correlation. If the model indicates that there is no relevance for a certain variable, sometimes less is more. So you don't want to have a variable that is not affecting the model to be considered. So you can remove it. We safely remove it. If we have data quality issues, we indicate to the customer which are the parts of the training data set that we need to be using, and then we reduce the data sets. That's why we use around 1 year of data. So from that, we get the correct data sets to train the model. And then we just go to the prediction, prescriptions, and again, supervised here. So something that I think is very important is the capability of the system to predict the process in a long term. There are systems that in the oil and gas, and where we have, let's say, fractionation system, might have more than 2 hours time, the residence time. So you take an action, and then you are going to see the result 2 or 3, 4 hours later. So we need to have the correct deep neural network that will capture that dynamic for those processes. So we need to be sure that we can create this. For example, in this case, this red line has to go all the way to that time. So we know that we won't face an issue in a particular system, because let's say that you keep feeding something, right? But then in the middle, you don't have any more capacity. Probably at that point, you will need to cut down the feed a lot, right? So you need to look ahead in the control horizon so that you avoid all of those problems. And this is something that, even though that looks like a simple graph, this is really what differentiates deep learning APC versus linear APC. In linear APC, there is just one curve. Is the gain response of the input versus output, or output versus input, and this reaction, if you see, depending on the capacity, if you're operating a low capacity, medium capacity, high capacity, your dynamics are going to change, and that's of course is because the residence time is changing and there are other factors. But the good thing, this is one of the good things. So you can capture, you are going to optimize better the process in all the ranges. So your model is not going to be a model just for one point in operation, but in the whole range. And then a second benefit of deep learning that we have learned is in linear APC, you spend weeks doing bump test, input and output response for all of the input pairs. Here, there is no bump test to do the identification of the process. And also something that is important is that, this is one of the things that we're doing for what everybody calls explainable AI. The customer is not they don't want to receive a model that is just a black box, because they say, I don't know how is that going to react. But if we have the input and output pair response, in a simulated form out of the neural network, then the customer says, yes, that makes sense. Or this one doesn't make sense. Let's re-examine, let's validate again, let's look at the data. And the same way, we can run the system for all of the history of the operation to find that gain that we saw. What is the distribution of that gain? Where do we typically operate the plant? And in this way, by looking at this, you can say, hey, yes, even though that the gain changes, it never changes sign, right? If it changes sign, then that's something just to be worried about, because now your action is going to be the reverse. You don't want that. So that's some other way to make it even more explainable. And then I have some use cases. People familiar with oil and gas automation, we have these layers of automation. At the bottom, we have the PNID controllers. I don't think that, of course, we can apply it there, but I don't think that that's where the benefit is in terms of AI projects. But what is inferentials, advanced of sensors, APC and RTO, those are the areas that for sure AI can benefit companies. Now we have, of course, the top, and those systems are mostly linear programming systems. Probably in the future, those can be also you can apply some genetic algorithms to do that, but at the moment, those are the layers where we're working. And then these are some examples of use cases that we are working on with customers. In this case, this customer has a reactor. They have a group of objectives. They want to increase the selectivity, but also they want to increase the throughput. And they want to find out what will be the optimal prescription of flow rate of the different reactants, what will be the optimal temperature and pressure of the reactor, of course, keeping in constraints other variables. And this might be a little bit simplistic because, of course, the variables are many more that you can have in your model. But this is a typical example. The important thing here is about objectives, right? The objectives typically they conflict with each other, so you can apply different weight factors for the genetic algorithm to find the optimum values. In terms of this is another process that is very common in refining and chemicals, petrochemicals, distillation operations, and in some cases multiple distillation columns. They are part of a large fractionation unit. These processes are nonlinear, right? And they can benefit as well. They benefit from having a good estimator. So here in this case, we want to control. Typically, we want to control the composition of the product. let's say we have n columns, we want to have the correct top compositions of every product. We want to optimize the feed so that we run at the limit without flooding, let's say, without flooding each of the columns or any other constraint. So that's one of the processes that we are working on as well. And then this one probably, this is another great benefit of deep learning is that typically models that are just physics-based for multiple units is going to be very hard to do, right? And it's very hard. You need to, eliminate some variables, make some assumptions, and of course you can create a linear model that will do something. But now what we are doing is that we are looking at the data of the end plants. Then we create a very big model, inferentials, and then we do the optimization in order to coordinate the operation of the 3 units. If we have a big optimization function that is looking at what is the revenue of each one, and it's going to find what is the best pace that you need to run at. All right, so that's RTO type of projects with AI. So these ones are basically the challenges and how we, I'm going to try to be brief. We have several challenges. When you look at the algorithm itself, yeah, you can take any algorithm and run it, and you will get something. But the question is that model will be able to represent the process, and we will be able to control it. And we need to do a few things, and we will get into those few things. We need to do data processing, eliminate peaks, right? We need to eliminate areas of downtime, of lack of, or places of lack of stability, find when we have broken sensors, all of that. But at the same time, we don't want to filter too much so that we lose the data, right? So it's a little bit of an art there. But you just have create the right pipeline to do that filtering, smoothing, alignment. Process data historians typically have different resolutions for different variables, so all of these things have to happen. Then training and model validation. This is basically when you train, you look at different models, you look at the errors, MREs, or other statistics to tell you, yes, we are capturing correctly the dynamics of the process. We look at the different scenarios, and we are also catching the direction, right? It's not only about being very accurate, but also capturing the high peaks in some cases. So that's another. This one was important. Long process delays. We have been implementing this in different industries. When you have long process delays, not all of the, let's say, a recurrent network might not work just in a very long delay process. So we might use, let's say, a LSTM or a group of LSTMs together in order to do that. So that's important to capture that correctly, to have a good time horizon when you're predicting, let's say hours ahead in the process. So that's basically solved by having the right architecture, and also when you have identified broken sensors, so that you can say, I'm not going to use this variable. Let's say DCB, let's say the ambient temperature is not working. Well, you can remove it, right? And then still do the optimization. And then traditional control, there is some control already, right? So typically AI will sit in the controls that the operators is manipulating, right? The operator is changing feed, changing recirculation ratio, something like that. Basically, we are going to be sitting on top on top of those, but we are not going to be touching the PNIDs, for example. But we will be monitoring anything that will prevent an PID from working. And then low frequency. This is important as well. There are many variables in the oil and gas industry that are not measured every minute. They are measured, let's say, every couple of hours, once a day. But we are controlling those, right? So the question is how we manage those. So the best way that is to use models that appropriately describe those, and then we can use these methods to create a synthetic data set that we can use in the dynamic model. So that's one way. That's one way to do it. There are multiple ML models here. Typically, random forests do very well, or linear models in terms of the inferential. So that's the challenge, but that's the way to go around it. And then what is called adaptive learning, right? So we know that there is a process fouling in heat exchangers. You might have a change in pattern in a specific sensor, mean shift. So all of those things, you need to be able to measure how good your prediction is. And we're monitoring that so that we can always retrain. Now, when we say continuous, in reality, technically it's possible, but it has to be tested, deployed, it has to be tested, quality assured, and deployed, right? So with all of those processes. And this is one of the, we're working in multiple projects in different, this one was the case of a yield optimization for a fractionation system. Again, the number of variables is very complex. It needed basically a high-level control, looking at the different units, right? In order to guarantee the quality requirements. And so this is basically the results, right? So it's yield increase, reduction in variability, and reduce the giveaway, right? So typically when an operator doesn't have a lot of control, they want to run, in a safe manner, right? To a certain variable, we can push that to a higher limit, and that's it. That's if you have any questions, I would be glad to answer.
Wow, that was great. Thanks. I guess my only question is, why aren't we doing this sooner? It seems so great.
Well, the thing is that's a good question. And one of the questions is that it takes time to replace technology, right? Well, technology is working, and then you need to look at the delta, right? And that's one thing. You need to have the justification, right? And the other one is training a deep learning model requires a platform. We have the technology to do that. Mm-hmm. Yeah.
I'm curious in the initial deployment. I've worked a little bit with APC. Do you still do the traditional step testing approach of APC, or are you able to eliminate that?
We are eliminating the step test.
Okay.
Yes, we have one of our APC engineers in the back, and then we can talk after. Yeah.
Other questions? Any questions from the virtual audience? Oh, okay. Cool.
So my question is, you were talking about some of the challenges and the issues of like broken sensors or defects in those sensors. Is there anything in this process that deals with deliberately malicious sensors, maybe compromised or attacks on the system?
Well, that will be more like an anomaly detection, probably. We have not done it for this type of project. People have not asked, but of course, if if you have a pattern that you feel that is normal, and then you can label what is not normal, you could have, let's say, a smart alarm, right? But that's technically possible, but we have not implemented in that way. Typically, in oil and gas, it's more an on-prem solution, so those type of attacks is going to be very rare, I would say. When we work with other industries that allows data to just travel, even control from outside, probably in that case, you might have something like that. But we haven't, we haven't, but that's a good idea, right? Okay. Yeah, I don't know if you have an application for that, or
I don't know.
Oh, okay.
I'll be doing a presentation on that in June at the Sensor Expo.
Okay, good.
On the use of machine learning. It's a completely different approach, but it would feed into your model saying, hey, we no longer, the confidence associated with this, whether it was intentional or unintentional, sensor drift can hurt you, or a bad calibration can hurt you just as bad as somebody who purposely tampers with it.
Yes, and then from there you can remove that DB. Let's say that you have a disturbance variable that you don't want to use, you just remove it, and then the model will continue.
Or maybe weight it less.
Yes, exactly. That's a good point. Yeah.
Great.
Exactly.
Other questions? Okay, thanks again, and thanks again for being the sponsor.
Thank you.
Okay.